Imagine you're standing in a park on a windy day. You can't see the wind, can you? There's no color to it, no shape. Yet you know it's there. You feel its push against your skin. Leaves skitter across the ground. Oak branches sway in a rhythmic dance. The wind is invisible, but its effects are everywhere. You don't need to see the thing itself to know it exists. You just need to witness what it does to everything around it. This idea guides scientists exploring the universe. This principle guides us on one of the grandest adventures in modern science. We are on a quest to understand a substance that, like the wind, is completely invisible. It passes through our bodies, our homes, our entire planet without leaving a trace. It doesn't shine, it doesn't reflect light, it doesn't cast a shadow. We call it dark matter, not dark like a lump of coal, dark because it is transparent to light and all electromagnetic radiation. A cosmic ghost, a silent partner, showing itself only by the gravity it exerts on visible things. Think of a grand cosmic ballroom. So, what exactly is this mysterious stuff we call dark matter? In the simplest terms, dark matter is a form of matter that does not interact with light or any other kind of electromagnetic radiation. This is its defining characteristic. The matter we are familiar with, the stuff that makes up you, me, the earth, the sun, all the twinkling stars, is called baryonic matter. It's made of particles like protons and neutrons. This ordinary matter loves to interact with light. It absorbs it, reflects it. That's why we can see it. Dark matter, on the other hand, is aloof. Light passes right through it as if it weren't there at all, making it completely invisible to our eyes and our most powerful telescopes. But just because we can't see it doesn't mean it has no effect on the universe. Dark matter has mass, and because it has mass, it has gravity. And gravity is the universal language of the cosmos. It's the force that pulls everything together, from the smallest dust particles to the largest galaxy clusters. Dark matter communicates with the rest of the universe through this one fundamental force. It is the unseen puppeteer, pulling the gravitational strings that choreograph the movements of galaxies. You might be wondering, if we can't see it or touch it, why should we care so much about dark matter? The answer is simple and profound, because it appears to run the show. Dark matter isn't a minor exotic component, it is the dominant form of matter. It is the silent majority. The galaxies we see, including our Milky Way, are just luminous decorations on a larger invisible structure. Like lights on a Christmas tree, dark matter is the tree itself, the hidden framework giving shape and stability. Without dark matter, the universe we see today would not exist. The Big Bang created a hot, dense, uniform soup of matter and energy. For galaxies and stars, gravity had to pull material together, but pressure from hot, ordinary gas pushed back, preventing collapse. Dark matter didn't have that problem. It didn't interact with light or pressure the same way, so it could clump earlier, forming deep gravitational wells. Those wells acted as cosmic seeds, attracting ordinary matter, which fell in and ignited the first stars and the first galaxies. Our case for dark matter isn't built on a single piece of evidence. It's a detective story with clues gathered from across the cosmos, all pointing to the same invisible culprit. The first major clue came from the way galaxies spin. In the 1970s, astronomer Vera Rubin was studying the Andromeda galaxy. She expected that stars farther from the galactic center would move more slowly, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. This is basic gravitational physics. The farther you are from the central mass, the weaker its pull. But that's not what she found. Instead, Rubin discovered that the stars in the outer regions of the galaxy were moving just as fast as the stars closer in. This was a stunning revelation. The only way to explain this was if there was a huge amount of unseen mass distributed throughout the galaxy, extending far beyond the visible stars. This invisible mass provides the extra gravitational pull needed to keep those fast-moving outer stars in their orbits. Another powerful piece of evidence comes from a phenomenon predicted by Einstein's theory of general relativity: gravitational lensing. Einstein showed that mass warps the fabric of space-time, and that this warping can bend the path of light. Massive objects like galaxies and galaxy clusters act as cosmic magnifying glasses. They bend the light from more distant objects located behind them, creating distorted, magnified, or even multiple images of the background source. By measuring the amount of this distortion, we can calculate the total mass of the lensing object. When we do this, we consistently find that the mass required to produce the observed lensing is far greater than the mass of all the visible stars and gas combined. We have even used this technique to map the distribution of dark matter in galaxy clusters, creating visible maps of this invisible substance. So, just how much of the universe is made of this mysterious stuff? The answer is both humbling and honestly, mind-boggling. When we survey the entire cosmos and add up all its ingredients, we arrive at a cosmic recipe that is profoundly strange. All the matter we've ever known, stars, planets, galaxies, nebulae, you and me, makes up less than 5% of the total mass and energy content of the universe. We are just a tiny, luminous froth on a vast, dark cosmic ocean. This realization is a true Copernican moment, displacing us not just from the center of the universe, but from its list of primary ingredients. The dominant material ingredient is dark matter itself. Our best cosmological measurements, confirmed by multiple independent lines of evidence like the cosmic microwave background radiation and the large-scale structure of galaxies, tell us that dark matter accounts for about 27% of the universe. That means for every 1 part of ordinary visible matter, there are more than 5 parts of dark matter. Our galaxy, the Milky Way, is not just a disk of stars. It's a small, visible component sitting inside a vast, spherical halo of dark matter that is 10 times larger and far more massive. But you know, the story gets even stranger. If ordinary matter is 5% and dark matter is 27%, that leaves 68% of the universe unaccounted for. This remaining and largest component is something even more mysterious: dark energy. While dark matter is a substance with gravity that pulls things together, dark energy is a mysterious pressure that is pushing the universe apart, causing the expansion of space to accelerate. It's a completely different phenomenon from dark matter, a sort of anti-gravity force embedded in the fabric of space-time itself. So, let's picture the universe as a pie chart. 95% of reality is composed of entities whose fundamental nature remains a complete mystery to us. We live in a universe dominated by the dark, and our journey of discovery has only just begun. The central challenge in the hunt for dark matter is its profound elusiveness. It is a true master of disguise, hiding in plain sight all around us. The reason it's so hard to detect is that it seems to interact with our world through only one fundamental force: gravity. It appears to ignore the electromagnetic force. It cannot absorb light, it cannot reflect light, it cannot emit light, we can't grab it with magnetic fields. It is transparent across the electromagnetic spectrum, from radio waves to gamma rays. It appears to ignore the strong nuclear force, which binds protons and neutrons inside the nucleus. This is why dark matter doesn't form atoms. It remains a diffuse, ghost-like cloud of particles. It also seems to have, at best, a very feeble interaction with the weak nuclear force. Together, these make it almost completely non-interactive with ordinary matter. Right now, billions of dark matter particles are streaming through your body, through the chair you're sitting on, and through the entire Earth, without disturbing a single atom, like ghosts passing through a wall. They don't bump into the particles around you because they don't feel the forces that cause collisions. They're only tethered to us by the gentle pull of collective gravity. Since we don't know what dark matter is, scientists have come up with a list of suspects, theoretical particles that could fit the description. The leading candidate for many years has been a class of particles known as WIMPs, which stands for Weakly Interacting Massive Particles. As the name suggests, these are hypothetical particles that are massive, perhaps 10 to 1,000 times the mass of a proton, and interact with ordinary matter only through the weak nuclear force and gravity. This weakly interacting nature would explain why they are so hard to detect, while their massive nature would explain why they provide so much gravitational pull. The WIMP hypothesis is particularly compelling because it arose naturally from theories beyond the standard model of particle physics, such as supersymmetry. The lightest of these supersymmetric partners would be stable, massive, and weakly interacting, a perfect WIMP candidate. But WIMPs are not the only suspects in the lineup. As experiments have searched for WIMPs and come up empty-handed, other candidates have gained more attention. One popular alternative is the axion. Axions are hypothetical particles that are incredibly light, perhaps 1 billion times less massive than an electron. They were originally proposed to solve a problem in the theory of the strong nuclear force. If they exist, they would have been produced in enormous quantities in the early universe and would form a vast, cold sea of particles, behaving gravitationally just like dark matter is supposed to. They are the opposite of WIMPs, extremely light but extremely numerous. There are also more exotic and perhaps less likely possibilities. One is that dark matter could be made of primordial black holes. How do you catch a ghost? The global scientific community is engaged in a multi-pronged attack on this problem, a great hunt that takes place deep underground in space inside powerful supercomputers and inside powerful detectors. The first strategy is direct detection. This involves building incredibly sensitive detectors, placing them deep underground to shield them from cosmic rays and other background radiation, and then waiting patiently for a dark matter particle to, by sheer chance, bump into one of the atoms in the detector. These experiments are marvels of engineering. They often use large vats of supercooled liquid like xenon or argon. If a WIMP were to pass through and strike one of the xenon nuclei, it would deposit a tiny amount of energy, causing a faint flash of light and knocking a few electrons loose. Ultra-sensitive sensors are poised to detect this minuscule signal. It's like trying to hear a single pin drop in the middle of a hurricane. So far, despite years of searching with ever more sensitive detectors, we have not yet had a confirmed, unambiguous detection. The silence from these experiments is, in itself, a profound clue, telling us that dark matter interacts even more weakly than we thought, or that it might not be a WIMP at all. The second strategy is indirect detection. Instead of looking for dark matter itself, we look for the products of its destruction. Some theories predict that when two dark matter particles meet, they can annihilate each other, producing a shower of familiar particles like gamma rays or neutrinos. We can then use telescopes, both on the ground and in space like the Fermi Gamma Ray Space Telescope, to search for an excess of these signals coming from regions where we expect dark matter to be dense, such as the center of our galaxy or nearby dwarf galaxies. Finally, there is collider production. At powerful particle accelerators like the Large Hadron Collider at CERN, physicists smash beams of protons together at nearly the speed of light. If we could produce dark matter particles in a collision, we would detect them as missing energy. The quest to understand dark matter is more than just an academic exercise. It represents a fundamental step in our cosmic self-awareness. Every great scientific revolution has been about revealing a deeper and often stranger reality hidden beneath our everyday experience. We once thought the Earth was the center of everything, until Copernicus and Galileo showed we orbit the Sun. We once thought our galaxy was the entire universe, until Hubble revealed countless other galaxies. The discovery of dark matter and dark energy is the next great humbling. Solving this mystery will transform our understanding of the universe. If we discover the WIMP, it will confirm theories like supersymmetry and open new particle physics. If we discover the axion, it will solve problems in the strong force and reveal new physics. If dark matter is primordial black holes, it will change our view of the early universe and gravity. It will change our view of the early universe and gravity. Whatever the answer is, it will be revolutionary. It will fill missing pages in the story of everything, from the largest galaxy clusters to our own solar system. This is why the search is so exciting. It is a journey into the unknown driven by curiosity. We build on the knowledge of those who came before us, Newton, Einstein, Vera Rubin, and push the boundaries of technology and imagination. It's a global, multi-generational effort that unites thousands of scientists to shine a light on the darkest corners of our universe. The answer is out there, written in the motion of the stars and whispered in the fabric of space-time. So, the next time you look up at the night sky, at the brilliant tapestry of stars in our Milky Way, remember what you cannot see. Remember the vast invisible halo of dark matter that holds our galaxy together. Be curious. Ask questions. The universe is waiting for us to uncover its deepest secrets.